See, I have a magnet placed here. This magnet exerts its influence in the region of space all around it. This influence is represented by a term, we have a term for it, and that is known as magnetic field. So magnetic field, it represents the strength and direction of the force which another magnet would experience when it is under the influence of this magnet. Of course, strength of the force exerted by this magnet, it's pretty simple to understand. As we move away from this magnet, the strength of this magnetic force would slowly and gradually, due to this magnet, would slowly and gradually decrease. That much we understand. What about the direction of the force exerted by this magnet? So what is the direction? Think about it. Let's say I bring another magnet close to this magnet. I bring the north pole close to the north pole of this magnet. I would immediately feel repulsion. Okay, so I would think that the force is going away from this magnet, emanating out from the north pole. That would be the direction of force, because that is the force which would push away another north pole. Of course, when I bring a south pole, it would feel attraction. South pole will feel attraction. So what should be the direction of force? What should we choose? We chose the direction of force to be the one experienced by the north pole, right? So if I bring a north pole, the direction of force it experiences would be the direction that we chose for the magnetic field of this magnet. So by convention, we have chosen the north pole to be our standard, and that is just a convention. So to plot the magnetic field of this magnet, what can I do? I can bring the north poles, various north poles. I can put the north pole at various locations and find out what is the direction and strength of the magnetic of the force experienced by that north pole. Our jobs actually have become a little simpler, because the needle of a compass always points in the direction where the force would be observed by the, or would be experienced by the north pole. So the needle of my compass, when I bring it close to the north pole, is pointing away from the north pole, and this would be the direction of force. Similarly, if I bring the needle of compass close to the south pole, it is pointing towards the south pole, and that would be the direction of my force. So it would be here pointing towards the south pole and emanating out from the north pole. I repeat this exercise on various points all around this magnet to find out the magnetic field exerted by this, sort of plot the magnetic field exerted by this magnet, and we would get a graph such as this. The next thing I do, I start joining these little arrows, the direction of forces, together to form complete loops. Okay, so that's what I'm doing. I'm joining the little arrows together to form complete loops. These loops are a good way to represent the magnetic field, and they are known as magnetic lines of force. So if I join these loops, how would they start? They would start from the north pole, they would complete this circle, go into the south pole. So there are few things that you have to understand here. These loops, they are completely closed. They start out from the north pole, go into the south pole, outside the magnet. Inside the magnet, they are traveling from south pole to north pole. The second property of these loops is that they never intersect, right? So if I draw a loop like this, there cannot be another loop crossing in like this. It is impossible, right? Think about it. At this point, we would have my needle, where would it point? It would point in two directions, right? At the point of intersection, the needle could point in two directions, the compass needle, which of course is not possible. So we are actually saved from that trouble by the property of these magnetic lines of force, that they can never intersect. So the magnetic lines of force go along each other, but they never cross each other. That's the second property. The third property of these magnetic lines of force, which you have to take care while drawing this, is that they are denser, they are more dense in the region where the magnetic field is stronger. So near the poles, my magnetic lines of force are very dense. As I go away from the poles, the magnetic lines of force slowly and gradually become rarer, they become less dense. And these magnetic lines of force, they are a very good way, they are an excellent way to to visualize the magnetic field. Of course, it's an aid in visualization. That's also something that we have to take care. There are no real magnetic lines of force in the space. That is not the case. Even between the magnetic lines of force, there is magnetic field. Magnetic field is there also. But it is just, we are representing the field using this visual aid, using these magnetic lines of force, and just to aid us, okay, just for our aid. Now, another interesting thing which happens, which we should understand, is what happens to these magnetic lines of force when I bring two magnets together. It is very interesting. Think about it. As I bring these two magnets close together, magnetic lines of force are created between the north pole of this magnet and south pole of the other magnet. If these magnetic lines of force were made of rubber, what would happen? The rubber would, of course, contract. It would be elastic. It is elastic, right? So if magnetic lines of force were elastic, they are made of rubber. These magnetic lines of force would contract and they'll pull the two poles, north and south. They will pull them together, which is, of course, the force of attraction which we experience when we bring these two magnets together. Similarly, what happens if I bring the like poles of two magnets together? The magnetic lines of force in that case act like imaginary balloons which are tied here at the ends, and they prevent, again they act as elastic, right? They act as in an elastic way, and they prevent these two poles from getting close to each other. They try to push them away. So that's a very interesting way to visualize how the magnetic forces actually happen by thinking about the magnetic lines of force being elastic. They are like rubber. One of the other things that you have to take care while drawing magnetic lines of force for a bar magnet is that they emerge only from the two ends of the bar magnet. Very few of them, if any, actually escape from the middle. So in the middle of a bar magnet, we don't really experience any magnetic force. The magnetic force is only concentrated at its poles. So this happens for one bar magnet. If I join two bar magnets, then also this is actually true. From middle of this bar magnet, I would experience very little force. I am experiencing no force from the middle of this bar magnet where I have now the joint of the two bar magnets. However, at the end of this bar magnet, the combined bar magnet, I am still experiencing quite a bit of force. So this new longer bar magnet which I have formed by joining two magnets, the magnetic lines of force again emanate only from the two ends and nothing emanates from the middle. So this is something that you should remember while drawing the lines of force.